Hi, in this video, we're going to continue OSPF v2 operations, establishing full state adjacency. Okay, so let's first talk about something called the OSPF router ID. OSPF routers need a way to uniquely identify themselves and everybody else in the OSPF routing domain. And they do that with something called an OSPF router ID. So how does Cisco iOS routers determine the router ID? Well, it can be the IPv4 address configured with the OSPF router ID command, and we'll see how to configure that in a later video. If the OSPF router ID command is not used, by the way, that is the best practice, then it will use the highest IPv4 address on any of its loopback interfaces. And if no loopback interfaces are on the router, then it will use the highest active IPv4 address of any of its physical interfaces. And that interface doesn't have to be enabled for OSPF. It just needs to be in the up and up state. Now I've been saying IPv4 address, and that's important because it's actually just a 32-bit value. The router ID, the OSPF router ID, is a 32-bit value. And as we'll see in OSPFv3 for IPv6, it's still a 32-bit value. So we'll talk about that later, but that's usually why the OSPF router ID command is important. We specify a 32-bit value. Actually, we do it using an IPv4 address, and we use that to specify the router ID. We'll define the router ID, excuse me. We'll talk about that when we get into the configuration. Okay, steps to OSPF operations with the OSPF states. Okay, so we're going to see that we need to establish router adjacencies. So as you can see in the right there, that's where we go from downstate, init state, two-way state. I'm going to do, I've got a little, a couple of slides on that I want to show you. Okay, so we go from the downstate to the init state. Again, I'm going to talk more about that, but that's kind of like, you know, you're sitting in a cafe and you're feeling a little down, and you say, you know what, I'm going to initiate a conversation. And you just turn to the person next to you, and you may not even know if there's a person next to you or not, but you just turn to your right and you go, hi, my name is Carlos. Or hi, my name is Maria. Okay, you just turn to either side of you and you just say hi. I'd say, hi, my name is Rick. Okay, so the two-way state in establishing is this neighbor adjacency is when the router next to this router goes, hey, you know, I heard you and this is who I am. It's kind of like, we're going to see this in another slide, but it's like, if we go back to, hi, my name is Carlos, hi, my name is Maria. Well, what happens if the person next to Carlos goes, hi, Maria, or hi, Maria, my name, or Maria would say this, I guess, or Carlos would say this, I'm sorry, hi, Maria, my name is Carlos. And she would go, hi, Carlos, my name is Maria. What you see in the difference between the init state and the two-way state is, hi, my name is Carlos, and hi, Carlos, my name is Maria. That's Maria coming back and saying, hey, I heard your name. Okay, it's like if I'm sitting in a cafe and I say, hi, I'm Rick, and the person next to me goes, hi, Rick, I'm Luigi. Oh, they heard me hearing my name in their hello makes me realize they heard my hello. All right. Okay, we'll see that more later here. Okay, we're going to be electing DR and BDR. That's for multi-access broadcast segments. We'll talk about that shortly. We'll be exchanging link states, synchronizing database, calculating the routing table, and maintaining the LSDB and routing table. So we're going to talk about these, but let's get back to that establishing adjacencies. So I said the routers begin in the downstate. So they initiate a conversation by saying hello and their router ID. Hello, I'm 10601. Okay, and this one might also do the same. Hello, I'm 10501. Now they go from the down to the init state either by an initiating hello or by receiving hello. Okay, so in this case, both routers are now in the init state because they've either sent the hello and or received the hello. All right, now that, let's say router B has received the hello from router A, it can say, hello, I'm 10601 and you are 10501. Router A goes, hey, I saw my router ID in your hello, so you must have gotten my hello. So I'm going to go in the two-way state because now we've got two-way communications happening. We can talk to each other. And by the way, hello, hello, I'm 10501 and you are 10601. And router B goes, hey, yeah, I saw in your hello to me my router ID. So that must mean you can hear my hello. I'm going to be in the two-way state also. Okay, so at this point, we've actually formed an adjacency. We're not fully adjacent, meaning our databases aren't synchronized, but we are adjacent as far as being neighbors, formed, and sometimes people call it a neighborship. So what happens after that? Okay, well, one of us has to begin with exchanging some link state information. So we exchange, I said, look, you know what? I'm going to start the exchange because I have a router ID of 10501. And router B goes, no, you know what? My router ID is higher at 10502. So I will start the exchange. So router B goes, here's a summary of my link state database. It's called a database description packet. And router A will go, well, then here's a summary of my link state database, just a summary. Now, by the way, that when they receive these database description packets, they're going to acknowledge that receipt of that by sending a link state acknowledgement. Okay, if there's any information in that database description packet, that DVD in that summary, that the other router doesn't have, oh, you sent me a DVD and I see you're sending me a summary, you know what? I need some details about some of those because I don't have those details from you or from any other router. So for anything I need details for, I'm going to send you a link state request, an LSR. Hey, I need the details for 10600/16. And the router will send back a link state update saying, here's the details for that link state. And by the way, both of these are acknowledged, both the link state request and the link state update with link state acknowledgements. Okay, once this process is done between the two routers for all their link state information, they then have their databases are synchronized. We both have the same information in our link state databases. Now we can use that information, run the SPF algorithm, come up with an SPF tree, and offer the best routes to the routing table. And at that point, when our link state databases are synchronized like this, we are what's called full state. Okay. So as far as dissemination of link state advertisements or these link state updates, OSPF does not send periodic updates like RIP. The link state updates or link state advertisements are only flooded throughout the area. We'll talk about areas later, but let's say the routing domain for now, when there's a change in topology. This also includes when the router first boots up. This is known as hop by hop flooding. So each router, when it receives LSAs from one neighbor, will flood that out all other interfaces to other neighbors. And there's actually part of the algorithm that there's a way that using some sequence numbers and such that it makes sure that it's not keeps on reflooding link state information that it had already flooded or already received. So that process does terminate. All right, so this link state information, how long does it live in the link state database? Well, OSPF decided that they're going to let it live just for 60 minutes. That's the maximum age that it will live. If it does not get a refresh within that time, the LSA is removed. So every 30 minutes, routers will flood their link states to other routers in the area. This is known as a paranoid update, meaning there's no real reason we need to be doing this because there's no change in the topology. But let's just go ahead and kind of reflood these every 30 minutes. It's why, just so, you know, kind of that's what kind of paranoid about it. Just make sure everybody's kind of got the same synchronized link state database. And that's why they have it age out after 60 minutes, because these things are being flooded every 30 minutes. In reality, you really don't need any kind of max age or paranoid update, the refresh, but it's a way to make sure that that somehow some link state information that might not have been either might not have been able to been received properly for whatever reason, a link being down or whatever, it might be the cause, got there. So it's, again, just for kind of a paranoid reason. Okay, if a link does go down, it actually sends the link state advertisement, says, hey, I'm sending this link state advertisement with an age of 60 minutes. That means remove it. Okay. So we talked a little bit about designated router, backup designated routers. Okay, so DR, designated router, backup designated routers. This is used as a collection and distribution point for link state advertisements sent and received on multi-access networks like Ethernet. Okay. So we have both a designated router and a backup designated router in case the designated router fails. All other routers on this Ethernet segment become what's called DR others. Okay. Now, adjacencies are still formed between all routers. Okay. And again, I want to mention something because this is kind of a point of confusion. This is only for sending LSAs. Okay. And we're going to see how this works in a moment. But if router R1 is going to send its LSAs to the DR, and the BDR will also get it, and that LSA will be flooded to all other routers on this segment by the DR. Okay, it's only for dissemination of link state advertisements. However, if in R1's routing table, it has a path to another network out here, network X, and that and its routing table says the best path is via R4. That packet is sent to R4. That's not an LSA. That's just a regular IP packet with data in it. It has nothing to do with link state advertisement. So regular IP packets are forwarded to their best next hop per the IP routing table. Again, this DR is just for disseminating link state advertisements, not for the actual routing of packets. Okay, I'm going to make sure we were clear on that. Okay, so R1 says, I have my link state advertisements, some changes in topology, or maybe I just joined the network or whatever it might be. So I'm going to be sending these to the designated router at multicast address 224006. That's all designated routers. Okay, so it gets sent, and the BDR also receives this. The DR is responsible now for forwarding that link state advertisements to all other routers on this Ethernet segment. And it does that by using the multicast address 224005, all SPF routers. So it's only one router doing the flooding. I kind of think of it like this. It's like being in the classroom. As the teacher, I might be the designated router. So if somebody comes up, tells me their name, then I can announce their name to everybody on the class. And we can do that one by one. That's a lot easier than everybody going up to everybody and announcing their names. All right. So how do we decide who is the DR and BDR? We're going to actually see the configuration in a later video, but for now, it's quite simple. So the designated router is the router with the highest OSPF interface priority. So we'll learn how to set that in a later video. The backup designated router is the router with the second highest OSPF interface priority on this segment. Yep. If OSPF interface priorities are equal, and because by default that they are all equal, then it uses highest router ID to break the tie. So whichever router has the highest router ID would become the DR. The next highest router ID would become the BDR, unless we set the OSPF interface priority, which we should do, best practice. Okay, the default OSPF interface priority is 1. Okay, so in this current configuration, the router with the highest router ID, which we're using loopback interfaces for right now, is the DR the highest. The BDR is the router with the second highest router ID. Okay, but we'll be talking more about that a little later. All right, so that's OSPF operations all the way to full state adjacency.